infinite of them. So the basis is infinite, though countably infinite, but still these are separate issues. We will not get into that. And the other thing I discussed was a definition of a linear operator. The important point to remember there is if I say something is a linear operator, that means I have told you everything associated with that operator operating on a vector in Hilbert space. Every vector on the Hilbert space, I should be able to tell you what that linear operator will do. If I have not done that, I have not defined my linear operator completely. So if you are enlarging your space, and if you want to take this linear operator to that enlarged space, then I am duty bound to say what it is going to do to the vectors in the newer space. Only then the operator gets defined in the newer space. This is a very important point to remember. Keep in mind every time. And you should go back. If something is an operator, what does it do? Then we can do it. So if it is every vector, we know that if I give a basis, any vector can be expressed as a linear combination of the basis vectors. So using the linearity of the operator, if I know what it will do to each member of the basis, I know what it will do to any vector. So my job simplifies to knowing what an operator will do to each one of the basis vectors. We normally choose the basis vectors as normal, orthonormal vectors. We orthogonalize it and normalize it. So all I need to know is what it does to every one of the orthonormal bases. Once I've done that, I've taken care of the definition of the vector. And if I choose another orthonormal basis, I know a new vector of the basis vector of the orthonormal basis can be represented in terms of the old one, because it's also a vector in the Hilbert space. So I should be able to represent it by the first orthonormal set. Therefore, I can connect the relation between the two different orthonormal steps. This is what we will do today first. But before I start writing that, let me write a few elementary things, which is all familiar to you, but still to get the notation going. I will just write it in two-dimensional space. I will write the following notation. Column vector. This is the normal notation used nowadays, not this 0 and 1. Quite often in physics, we use the following notation. I will write it off very soon. And this to represent the z component of spin, the way which was discussed today by Professor Ashok Kapoor earlier in the morning. And instead of that, I will be using this because this notation is now getting standardized in quantum computation and quantum information. So I will continue to use this notation. Okay. The reason for that was, remember my sigma 1, sigma 2, sigma 3, which I will keep it here. So this 0 vector is an eigenvector of sigma 3 operator with eigenvalue 1. The 1 vector is an eigenvector of sigma 3 with eigenvalue -1. So that's why we normally use it to be pointing out spin up for this vector and spin down for that vector. All this I'm sure you people are familiar with. And now I will write down the dual vector to 0, which I will represent by 1, 0 and 1 by 0. So if I take any arbitrary vector alpha 1, alpha 2 in this space, and another arbitrary vector, let me call this alpha, and beta is another arbitrary vector, then the scalar product beta alpha would be beta 1 star, beta 2 star, alpha 1, alpha 2, which is beta 1 star, alpha 1 plus beta 2 star, alpha 2. And if beta alpha is 0, then alpha and beta are orthonormal. Okay. I can write down some normalized vectors which will be useful to me. I will write it as plus x is 1 by root 2, 1, 1, minus x. Quite often this also is written as sigma x, sigma y, sigma z. So that's 1. We have done this yesterday. One can verify the following. These are eigenvectors of sigma y with eigenvalue +1 and -1. These are eigenvectors of sigma x with eigenvalue +1 and -1. This is a scalar product of two vectors with different eigenvalues of sigma x. Similarly for this for sigma y, and that's why this is 0. You can easily verify this. For example, let me just verify one. Let me verify the second one. What is +1? I have to take this, all right, 1 by root 2, 1 minus I. And then what is minus y? Is that. So I will write it as plus y minus y. 1 by root 2 and 1 by root 2 is half. And then I write down 1 minus I, 1 minus I. Let's multiply it. When I multiply this, I get 1. And then I have minus I, minus minus becomes plus, I squared is -1. So this is 1 minus 0. I'm sure these things you people know, but for a matter of systematic thing, I'm just writing it out. Okay. This is the two-dimensional space. So this vector, the first one which I wrote 0 and 1, they're also orthogonal to each other, form an orthonormal basis. These two vectors also form an orthonormal basis, a different one. Similarly, of course, I can have infinite of them. I've just chosen some of them. Now take a vector, some vector alpha. I can write it in terms of this basis. I can also write it in terms of this basis. They are related. How do I relate them? I can write plus x plus x is a vector in my space. This is a basis, so I should be able to write it in that. And that is very simple. I have it here, 1, 1. So it is 1 by root 2, 0 plus 1 by root 2, 1. So this expression here, I can write it as d1 times. I to take the root 2 outside, 0 plus 1. For d2, for this minus x is 1 by root 2, 0 minus 1 by root 2, 1. So I will write that as plus d2 times 0 . Yes, somebody is asking a question whether this is the bra and the ket notation. The answer is yes. It's the same notation which Professor Kapoor was also using. Okay, now all I have to do is collect my 0 to make it C1. So I collect from here, coefficient of 0 is C1 from there is equal to D1 plus D2 by root 2. And C2 is D1 minus D2 by. Or I can write down D1 and D2 in terms of C1 and C2. It doesn't really matter. I can go from one orthonormal basis to other orthonormal basis. And this is the procedure to do it, the way I have said it. That is, you express each one of the orthonormal basis vector of this in terms of the other basis. and then that is a linear vector. So I can add it up and find out the answer to the previous case. We will do it in a little bit more general. Now I want to talk about matrix elements. But before I do that, I want to be sure this is okay. I'll just wait for half a minute or so before I proceed. All right. Now I want to write matrix elements of the vector of an operator. I will write it like this. Matrix representation generally. Consider an operator. I'm still talking in terms of two dimensions. I've said that I know, if I tell you the operator, I know what it does to any vector in the Hilbert space. So I certainly know what it does to this. This is another vector in the Hilbert space, two-dimensional space, which I should be able to expand it in terms of 0 and 1, and I will write it as A 0 0 0 plus A 1 0 1. Be careful of my notation. 1 comes here, not there. Then A, when it operates on 1, gives me A 0 here, 0 1 plus A 1 1 1. Notice, why do I use this notation this way? Take 0 A 0. That these are complex numbers. So when I write the bra vector here, this will become 0. So this will just be A 0 0. Similarly, if I write 1 A 0, notice if I take the scalar product with 1 here, this is the term which will survive, which is A 1 0. Notice this 1 is here, 0 is there. That's why I have made this choice. Be careful, you should not write it as 0 1. Then in that case, that will make a transpose situation. And now the rest of them are clear. And so I will write down A as A 0 0, A 0 1, right? And I will write A 1 0, A 1 1. Right? Check. This is my A. Let's operate on A on 0. Let's see whether this works out. A 1 0. When it operated, I get A 0 0. Did I write it wrong? 0 1 1 0. Let me just see. What did I do? A 0 1 0. So A 1 0. Yeah, this is 1 0. I have to operate it on 1 0. So I get A 0 0 here, and that is 0. I get A which is A000 plus A1. And similarly for the other cases. So this is the way, this notation, and this is what is consistent. Keep this in mind. Now, next very important thing, quite often we may prefer to work in some basis and the experimentalist or somebody else may have to work in another basis because that may be more convenient for him. Under different circumstances, this can happen. I will give you examples of that. So we must be able to relate the matrix representation in terms of one basis into matrix element of representations in another basis. And that goes through, I will be discussing orthonormal basis that is done by a unitary transformation. Let us see how that works. Now I'm going to go beyond 2 dimensions because it's as general. I wrote down 2 only to illustrate it. Now I will write down for a more general case. Okay. 2 bases. Orthonormal basis. EI I 1 to n, Fi I 1 to n. Of course, they are orthonormal, so I have the relation Ei Ej is equal to Fi Fj equal to beta Ij. Now take F, the vector F. I can express this in terms any particular vector F. I can express this in this terms of E's. So I write down summation j u j I e j going from 1 to n. I will write down f of k. I have to take complex conjugate, and instead of calling this I, now I'll call it k. That will be summation over L going from 1 to n. I will use a different symbol. Instead of here, I will write down U star LK E. Now I multiply these two, get the scalar product. This must be delta Ik, which is equal to summation L going from 1 to k n U L k star, and this number I will EL I have written down, and then I have to write for Fi that I write U j I, that is summed again from 1 to n Ej, and I forgot to write my EL. What is this? This is orthonormal set. So this is delta Lj. So what do I get? I get delta. I get from here delta Ik equal to sum over ULK star UJ I times delta Lj. This sum is over L and I, not I, L and J. If I now sum over J, only term with L will contribute, J equal to L. So this becomes sum over L, U L K star U L I. Which I will continue here. I can write down this LK as KL and that will be transposed. So this will become L U dagger K L U L I, which is equal to sum is over the here matrix multiplication U dagger U K I. So delta Ik is equal to U dagger. So only when K equal to I will this be 1, otherwise it will be 0. So I have proved the result after doing all this algebra. I have proved, maybe I'll rewrite it when I need it. I have proved the result. U dagger U is equal to I. Only when I equal to K, this is an identity operator, and this is what is the unitary operator. So a very important result. The result is if I take two orthonormal bases, a transformation from one orthonormal basis to the other is implemented by a transformation which is unitary. Okay. So that is the important message here, and let me write that out. This is the important statement. So this is as far as the basis is concerned. I go from one basis to the other by unitary transformation. Let us see what it does to the matrix element of a linear operator. Next. Okay, let me start with that. Let me write down V at A, EI, EJ, which I had called AJI. Now I'm going to write FK, AFL. This I will call A tilde, same A tilde KL. So I want to find a relation between these two. Okay, how will I do that? I write down F in terms of E, which I've already done. I know how to do that. So this will be written as summation L P L, this one, U dagger K L A U P L, not L. I don't. Oh, L is not a good thing here to use. R, and then I have U. What should I write? U P L C. Here. So this is ERP. So this is U dagger KR ARP UPL. So what do you conclude from there? You conclude from there, this is URR summed, and these are matrix element of A. So I get this matrix element A. If I write this as a vector, matrix element as some matrix A dagger in the F representation, this is U dagger A. U dagger A U K L. Notice this is K, this is K. This is L, that is L. The one which I have written down is K L. This is how the two get related. Hamiltonian does not completely specify the system. What it does, it specifies the time development of a system if you give me the initial state of the system. To specify an initial state of a system, I must specify its vector in the linear vector space. Hamiltonian does. Supposing I say its Hamiltonian is that of a particle in a box. I don't know whether it is in the ground state, first state or not. Same way for a hydrogen atom. I can write out P squared by 2m minus E squared by 4 epsilon naught R. That does not yet specify the state of the system. Okay? So Hamiltonian only tells you the energy levels, possible energy levels, and the time development. And it may not be an eigenstate of energy, the system. It could be a linear combination of eigenstates of energy. It may not have a definite energy. All these are possible, and experimentally people get it. Such states. They have been constructed. Okay. Now I'm going to switch gears and make some general statements. Then we will see how they are useful to you. The skills of handling matrices is very important in doing calculations in quantum mechanics. Even if you do experimental work and if you want to generalize, these skills, they are the basic skills which one should get, and please ensure that you are comfortable with them. That's extremely important. Okay. Now, let me talk about Hermitian matrices. What is the condition for Hermitian matrix? It is X H Y is equal to Y H X star. Normally I would have written a Hermitian conjugate here, but since it is Hermitian, Hermitian conjugate of the matrix is the same as the matrix. So now let us look at the matrix. Say we have a two-dimensional space. I will concentrate on two-dimension right now. So E1, E2 forms the basis. So what does I can write down for X and Y? So the first one I will write is E1, that is H11 equal to E1, H1 EM star, which means H11 is real. Similarly, H22 is real. H12 is E1 H E2 equal to E2 H E1 star H. So my Hermitian matrix here consists of H11 real, H22 real, H12. These two elements are complex conjugate of each other. Now I am going to ask you people a question and pause. How many degrees of freedom are available to me? How many real parameters are there to describe a 2x2 matrix, Hermitian matrix? Those of you who want to answer can answer me in the chat mode. I will wait for half a minute. Yes? Yeah, please put the answer in the chat mode. It's easier for me.
Yes, Professor.
Yes.
I think there's no question. You can keep. There's a question. Thus mentioning of Hamiltonian.
How many independent parameters does a 2x2 Hermitian matrix have? Real parameters.
Participants, please unmute your mic and convey the answer, please.
How many?
4 parameters.
4. That's correct. How do you see that? The thing is, I have one real parameter here, one real here, one complex parameter here between the two. One is a complex one. So I have 1, 1, and 2. That makes it 4. Let us answer the question for n dimensions. All these are real. N real for diagonal. How many are left? Total number of elements is n squared. I have subtracted n from here. So I am left with n squared minus n parameters, out of which this set is complex conjugate of that. So I just need so many parameters times 2. Because so many complex numbers here. N squared minus n by 2 complex numbers. So the number of parameters is n squared minus n, and I add the 2, I get therefore h n cross n as n squared real parameters. In general. Now, let's look at the 2 by 2 a little bit more. Let's try to specify all the 4 parameters. The 4 parameters, I will write it down in terms of 4 matrices. I is one matrix, 1, 0, 0, 1. Sigma 1 is another matrix, 1, 1, 1. This is a Hermitian matrix. 2 is 0, I, sorry, minus I plus I 0. Sigma 3 is 1, 0, 0, minus 1. How do I know they are linearly independent? That if I write this, I have 4 of them. How do I check linear independence of these? Again, the same way as I do there. I write down C1I plus C2 sigma 1. Or let me write 0 here, 1 here, sigma 2 C2, C3 sigma 3. Let us check. Given this equation, do I get C1, C2, C3, C, all of them to be 0? Let's substitute this. I get C2 plus C3. And then I get C1 minus IC2, C1 plus IC2, C0 minus C0. This must be equal to 0, 0, 0. So what do I get from here? I get C0 plus C3 is 0, C0 minus C3 is 0. So I get C3 plus C is 0, C0 minus C3 is 0. So I get C0 is 0, C3 is 0. So it's gone. What about here? C1 minus IC2 is 0, C1I plus, these are real constants I am taking. If I don't take real constant, they will not be a Hermitian matrix because these are all Hermitian matrices. So I get C1 equal to 0, C. So they are all linearly independent. You cannot write any more linearly independent vectors in 2 by Hermitian matrices in 2 by 2 space. That's it. Nothing more. Now, there are some very interesting properties of this, and let me explain that. A trace of a matrix A is equal to sum of all its diagonal elements. You can check here, trace, let me call this sigma 0 equal to I, it's convenient for me. Trace sigma mu is 0, mu is 0, no, trace mu is not 0, trace I is 0, sigma 1, sigma 2, sigma 3, I 1, 2, 3 is 0. Of course, trace sigma 0 is 2. Sum of the elements. There is also some relations among sigma. You people should know this like you know your sine theta and cos theta. It's extremely important to keep this in mind. Sigma I, sigma j, ij 1, 2, 3 plus sigma j, sigma I is 0. I not equal to j. In fact, best is to write it as 2 delta ij. And next is sigma 1, sigma 2 equal to I, sigma 3. Sigma 2, sigma 3 is I, sigma 1. Sigma 3, sigma 1 is I, sigma 2. Notice sigma 1 and sigma 2 anti-commute with each other. So this is minus I sigma 2 sigma 1. This is minus I sigma 3 sigma 2. This is minus I sigma 1 sigma 3. These are important relations.
Last line.
Yes.
Last line which you have just written, I should not be there.
Where?
Last expression.
Oh, here.
Yeah.
Sorry. Thank you. Okay. So now take the Hermitian matrix. Oh, now one more thing here. Trace of sigma I sigma j. One more. Okay, let me also write that down coming from here. If it's I is equal to j, this is sigma 1. Supposing I equal to j equal to 1. This is sigma 1 squared plus sigma 1 squared equal to 2. So I get sigma 1 squared equal to sigma 2 squared equal to sigma 3 squared is equal to I. Then I have a very important relation. Trace of sigma I sigma j is 2 delta ij. Let us verify this. If I put I equal to j, say, let me say sigma 1 squared, this is I, and trace of I is 2. I equal to j equal to 1. If I is equal to 1, j equal to 2, this is sigma 1 sigma 2, but sigma 1 sigma 2 is I sigma 3. But trace of sigma 3 is 0. Why? Sigma 3 is 1 minus 1. Similarly, you can verify every one of them when I is not equal to j, it will be 0. This is like taking a dot product between I dot j, I dot k, k dot j. It can be thought of as a dot product. A generalization of a dot product that we do, scalar product, when we deal with ordinary vectors in the matrix space. In the matrix space in which we are talking about Hermitian matrices. So one can think of sigma I, sigma 1, sigma 2, sigma 3 as an orthonormal basis in the 2 by 2 Hermitian space. So now let me write down any matrix H as C0 sigma 1 0 plus C1 sigma 1 plus C2 sigma 2 plus C3 sigma 2. How can I locate each one of them? I can write down trace of H C0. Sorry, sigma 0. Sigma 0 is identity matrix, remember. So when I write this as C0, trace sigma 0 squared plus C1, trace of sigma 1 sigma 0 plus C2, trace of sigma 2 sigma 0 plus C3, trace of sigma 3 sigma 0. This is identity matrix. So this is just 2 C0. This is identity matrix. This is trace of sigma 1, but trace of sigma 1 is 0. Similarly, this is 0. So I get C0 as this object. It is very similar to what we do. I write a vector as axi plus ayj plus azk. Then when I take the dot product of this, I pick up x. Here the dot product is replaced by taking the trace with that appropriate element. I would correspond to sigma 0. I take the dot product. I take the trace. So you see the parallel on how it works. So in general, the answer is this. Trace x sigma I is equal to half CR. And trace x sigma 0 is equal to half. We will need this when I discuss density matrix tomorrow. Okay, next 5 minutes I want to discuss something else. Functions of matrices. I will concentrate on talking about Hermitian matrices, and then one can see how it can be generalized to other ones, because we are talking in terms of Hermitian matrices. I will take about 5 more minutes and then stop. But before I rub this off the backbone, if you have any questions or any comments, please put it on the chat mode, and I would like to see. I'll wait for about a minute.
So thank you, sir. So the participants, if you hand out, please mention your questions in the chat box, please.
No, I will take another 5 more minutes, please.
Yes, sir. Yes, I'm just waiting for the.
But before that, I thought whatever I have said, if there are comments or questions or any other things which they would like to discuss associated with this, I'll be.
Sir, can I ask a question?
Please, can you put it on the chat mode, please? It'll be easier for me.
Okay.
Okay, as you're putting it, I will rub this off and write down what I wanted to start. Please ask the question. All right, I'll write here. Yeah, if you want to ask the question directly also, I will try to understand. Please say that. You have done it? No.
No, sir, it's quite a lengthy one. I'll just type it and put it in the chat box.
Oh, you put it in the chat box? I have not seen it. Yeah.
I mean, sir, I'm typing it. I mean, it's a lengthy
Oh, you're
one.
typing it. Okay, please do.
Okay.
Okay. For two state vector and a unitary operator u, then the scalar product of u acting on A and B has the same scalar product of A and B. Two state vectors A and B and a unitary operator u and a scalar product of u acting on A and B. I don't, when I, let me write it down. State, I will write it like this, and another one like this. U is an operator, right? And
Yes,
then
sir,
you have
it's a
U,
unitary
which is a
operator.
unitary operator. And what is the statement? A
I mean,
unitary
now
operator
U is acting on
then
A and B.
acting on A and B is a scalar product of A and B. No, if I write U A B, this is not equal to A B A. What is equal to B A is U A if it is A prime, U B if it is B prime, then B A is equal to B prime A prime. That you can see, because if I write B prime is B U dagger. So this becomes B U dagger UA. And this is a unitary you said, so this is B.
Okay,
So
so
the
my
scalar
question is
product under a unitary transformation, it means I must transform both A and B, then it will be equal.
my question is not, it's like the same thing. I mean, U is acting on A and B. So I have this like U acting on
Oh,
vector.
you acts on A and B, then of course you are right. You're okay.
Okay. So my
Yeah,
question is like an operator is acted upon a state vector. Still after the operation also, if you take the scalar product of these two, I mean, it's like some operation is acting on a vector, na?
Correct.
So like, I'm just curious to know about the physical meaning, like some operation is done on the state vector. Still after the operation, these two operators, like, I mean, the scalar product of these two state vectors is the same as the scalar product of the initial state vectors.
No, so long as the operations are unitary, it will be, the scalar product will be preserved.
Okay, it's like I mean, there is no physical meaning for this one.
Right. In fact, the time evolution of any wave function given a Hamiltonian, which is Hermitian, is a unitary transformation. That's why the probabilities are preserved.
Okay, sir.
Probability is nothing but the scalar product of psi with itself. Right? In a state.
Yeah.
Okay, now, sorry. Now let me write down. Let me take an operator h. I can write h squared. H squared is very simple. H into h. Similarly, I can write h2. Now I can define e to the x. How do I define e to the x? The same way I define e to the x in real numbers or complex numbers. So I will write this as h to the 0 plus h divided by 1 factorial, 0 factorial, and if I had alpha there, some complex number, this is how I will define it. How will I define sine of h? Again, I will write it as I know how to do it. Similarly, cosine of h and so on. There's only one problem, and that problem is associated with log. Can you expand log x? You cannot expand it about x equal to 0 because log 0 is minus infinity. So what you have to do, you have to write it as log 1 x 1 plus x minus 1 and expand about 1. Log 1 is 0, no problem. So I can write this as x minus 1 plus x minus 1 squared by 2 factorial, etc. I do the same thing here. If I have a log x, I write this as log I plus h minus I. And then I proceed to expand it about h minus I. Use this. One important question. When I make an expansion, the infinite series, is it convergent or not? That will depend on h. And in some cases it is, some case for exponential it is. No, usually there is no problem, but every time you have to check, and that check is not easy. That requires a reasonable amount of analysis, both real and complex, before you can be sure that your expansion is valid. But we will be using these sometimes, and then you will see how it works. Okay, I think I'll stop for today here and then meet tomorrow, and I will discuss a little bit of density matrices tomorrow, connection to some physics. Okay. So if you have any questions, you can ask, otherwise I'll stop. Okay, then, bye now. I will see you tomorrow again at the same time.
Yes, sir. Thank you, sir. Thank you so much, Professor.
You're welcome.
Participants, any queries, any particular queries? Or any comments?
All right.
Okay, sir.
Okay, bye.
Okay, once again, thank you so much, sir, for your innovative lectures. And participants will meet once again for the tomorrow session, sharply by 10 a.m. So the feedback link for today's session will be shared to you shortly by WhatsApp.
Sure, sure.
And participants are requested, those who are present here today's session, are requested to mark their attendance online. So once again, thank you, sir, for your kind lecture.
Okay, bye.
Thank you, sir. Vijayaranga sir, line இருக்கீங்களா sir?